Welcome back. In this video, I'm going to solve two important exercises of chapter 1. Exercises 13 and 14. Exercise 13 is an exercise about the distance from a point to a set in a metric space. So what is the idea behind? If you can draw a picture if you like. So consider just in the plane a set A and the point, for example, X outside A. There is a shortest path from X to A. This is the meaning of infimum. Now, the infimum is not really not necessarily a minimum, but in some sense, it's something that minimizes the set of all distances from X to points in A. Okay, so in some sense, it's the shortest path. So we have first question. We have to prove that. So observe that if X is in A, then dxa is 0 already because just take y equal a. Okay, and you can also prove that if x is in a bar, then the distance is 0. But we have to prove here the inequivalence between x in a bar and the distance between x and a is 0. Second question, we have to prove that the distance from x to a minus the distance from y to a in absolute value is less than the distance from x to y. So this is a kind of triangle inequality, if you like. And if you know already what's the meaning of a Lipschitz continuous function, this means that the function f of x equal dxa is Lipschitz continuous with constant 1. And we shall get back to this later. Third question, when the set gets bigger, the distance becomes smaller. So here also we can draw a picture in the plane. Just picture a set A contained in a set B and the point x outside. So when the set gets bigger, the distance from X to the set becomes smaller, actually, not the other way around. Question D, show that the distance from X is the same as the distance from X to the closure of A. And the last question, A bar equal B bar if and only if for every point in the space, the distance from X to A is equal to the distance from X to B. Okay, so first question. Okay, maybe it's preferable to split the equivalence into two implications. But I did it here actually as a series of equivalents. So we know by proposition 1.8 that a point X is in the closure of A if and only if every neighborhood of X meets A, or equivalently, every ball of center X meets A. Now, what does this mean? It means that I can find a point in the intersection. A point Y is in the intersection if it is in A and it is in the ball. So if Y is a point in the intersection, then Y is in A and Y, the distance from X to Y is less than epsilon. Okay. Now, this is equivalent actually to saying that the infimum of the set of all distances from X to elements in A is 0. Why? Because if this is true, the infimum is less or equal than dxy, so it's less than epsilon. But since epsilon was arbitrary, we conclude that the infimum is 0. And conversely, if the infimum is 0 by a property of the infimum, given epsilon positive, I can find y in A such that the distance from x to y is less than the infimum plus epsilon, which is epsilon. And that's it. So this is equivalent to saying that the distance between x and A is 0. Second question, pick an arbitrary point z in A. And therefore, since dxa is the lower bound of the set of dxy, y in A, so in particular, dxa is less or equal than dxz. And by the triangle inequality, dxz is less than the distance from x to y plus the distance from y to z. So if we subtract dxy, we get this identity with this inequality. Now, this is true for every z in A. Therefore, this is a lower bound of the set of dyz z in A. But the distance from y to A is the biggest lower bound. Therefore, this lower bound is less or equal than the infimum, which is dya. So subtracting dya and adding dxy, we get dxa minus dya is less or equal than dxy. And now, by symmetry, since x and y, this is true for every x and y. So if I interchange the roles of y, x and y, I get dya minus dxa less than dyx, which is dxy. And therefore, the absolute value of the difference is less than dxy, because the absolute value is either this or that. And in both cases, it's less than dxy. Okay. Question C, almost trivial. If A is contained in B, then the set of distances of elements of the form dx, y in A is contained in the set dx, y in B. Now, when the set gets bigger, here we are dealing with subsets of the real line. So when the set gets bigger, the supremum gets bigger, but the infimum gets smaller, because we explained that last semester. So pay attention to the order of sup and inf. So therefore, the infimum of the bigger set is less or equal than the infimum of the smaller set. And that's it. So dxb is less or equal than dxa. And as I told you, you can draw a picture to convince yourself what does it mean. So when the set gets bigger, the distance from x to b gets smaller. Question D, dxa bar equal dxa. So here by C, we already, since A is contained in a bar, then dxa bar is less or equal than dxa. Now to prove the converse, we use a common strategy in proving inequalities. We prove that dxa is less than dxa bar plus epsilon or 2 epsilon, or just an arbitrary positive number. We encountered this before. So pick up a positive number epsilon and use the familiar property of the infimum. The infimum plus epsilon is not a lower bound, so there exists y in a bar such that dxy is less than the infimum plus epsilon. Now, since y is in a bar, by proposition 1.8 again, the ball of center y and radius epsilon meets A at some point z. So the distance from y to z is less than epsilon. And now I just use the triangle inequality. So dxa is less or equal than dxz because z is in A. So this is a lower bound, and this is an element in the set. So, and now use the triangle inequality. dxz is less or equal than dxy plus dyz. And dxy is less than dx. Yes, this is a bar, sorry. So put a bar here. So dxy is less than dxa bar plus epsilon. And dyz is less than epsilon. So I get dxa bar plus epsilon plus epsilon. Okay, so once again, this is a bar. Therefore, dxa is strictly less than dxa bar plus 2 epsilon. Since epsilon was arbitrary, we conclude that dxa is less or equal than dxa bar. Okay, last question, straightforward, because if a bar equal to b bar, then dxa bar equal dxb bar, and therefore dxa equal dxb. Conversely, how to prove that a bar equal b bar if dxa equal dxb? Double inclusion. Take x in a, but it's symmetric, actually it's enough to prove with just one inclusion. Pick an arbitrary element x in a bar. Then by the first question, dxa is 0. But since dxa equal dxb, then dxb is 0. And by property 1 as well, x is in b bar. So a bar is contained in b bar, and by symmetry, b bar is contained in a bar since they play the same role, and therefore we have equality. Okay, so this concludes exercise 13. Next exercise is about the diameter of a set. Okay, so this is actually how do you define the diameter of a set? Is in some sense the biggest path joining 2 points in A, or the maximum distance, if you like, between 2 points. Now it's a supremum because it need not be a maximum. Okay, and this is the purpose of the first question. If you take just the interval 0, 1, 0 and 1 are not in the set, so there are no points in this set whose distance is exactly equal to 1. But I can find 2 points whose distance is as close as 1 as I wish. So the diameter of 0, 1 should be clearly 1 minus 0. And more generally, the diameter of an interval AB is B minus A. Okay, second question, the diameter gets bigger when the set gets bigger. The diameter of A is the diameter of its closure. The diameter of any ball of center A radius R is at most 2R. Same thing for the closed ball. But these inequalities may be strict, so equality may fail. And the last questions are about boundedness. A set is bounded if and only if it's, well, by definition, it's if the diameter is finite. Because here I'm using the supremum in a generalized sense, because it's possible that this set is unbounded, so the supremum is plus infinity. So for example, what is the diameter of R? The diameter of R is the supremum of x minus y, xy, and R, and this can, so the supremum is plus infinity, because we can take x and y as far from each other as we wish. So it's possible. So here, this diameter, this quantity belongs to 0 plus infinity, closed in both ways. Okay. So first question: how to prove equality, double inequality? So take 2 points x and y in 0, 1. Then their distances, the distance between x and y in absolute value, is actually less than 1 strictly. So when I take the supremum, I get less or equal. So this is true for all x and y. So the supremum is less. So 1 is an upper bound. So I get the first inequality. The diameter is at most 1. And then I use the familiar strategy. So pick a positive number epsilon and take epsilon x epsilon as close as you wish from 0. So x epsilon is epsilon, and take y epsilon to be very close to 1. Of course, I should take epsilon less than 1/2 in order to ensure that, so so usually epsilon is small. Okay, and therefore the distance between x epsilon and y epsilon is 1 minus 2 epsilon, of course, provided epsilon is less than 1/2. Okay, but the diameter of 0, 1 is bigger than this quantity, or equal. So it's bigger or equal than 1 minus 2 epsilon. And since epsilon was arbitrary, we conclude that the diameter is bigger or equal than 1. So we have double inequality and therefore equality. Okay. Second question, straightforward. When this should be B, actually, not A. So when the set gets bigger, the set of distances from x to y, x, y, and A is contained in the set of distances from x to y, x, y, and B. So taking the supremum, we get diameter of A less or equal than diameter of B. Okay. And now, third question, diameter of A and diameter of A bar are the same. So by B, the diameter of A bar is bigger or equal than diameter of A. To prove the converse, we take epsilon as usual. And by a property of the supremum, when I subtract epsilon from the supremum, it's no longer an upper bound, so I can find an element in the set such that the xy is bigger than the supremum minus epsilon. So same thing. And now, since x and y are in A bar, I know that I can find an element x prime. So the ball of center x and radius epsilon meets A at some point x prime. And the ball of center y and radius epsilon meets A in a point y prime. So dx x prime less than epsilon and dy y prime less than epsilon. And now I just use the triangle inequality. The distance between x prime and y prime by the triangle inequality, or if you like, start from this, dxy is less than dx x prime plus dx prime y prime plus dy prime y. So you get epsilon plus dx x prime y prime plus epsilon. So you convince yourself that this is just the triangle inequality, actually, and I'm using these facts. Okay. So, and therefore, but now the diameter of A, since this is an element, so since x prime and y prime are elements in A, the diameter of A is bigger than this. Okay. And the dxy minus epsilon is bigger than the diameter of a bar minus epsilon. So I get minus 2 epsilon minus epsilon, so I get minus 3 epsilon. And you conclude in the usual way, diameter of A is bigger or equal than diameter of A bar, and therefore we have equality. Okay. Question D, the diameter of a ball of radius r. This is straightforward, because if we picked any 2 points xy in the ball, the distance to the center is less than r. So dxa less than r and dya less than r. So by the triangle inequality, dxy is less than 2r. And since this is true for all xy, taking the supremum, we get the diameter, which is the supremum, is less or equal. So always when you take the supremum or the infimum, large strict inequalities become large inequalities. So the diameter of this ball is less or equal than 2r. Okay, now we could have equality actually, and can give an example actually. But here we have to give an example where we don't have equality. So we get the diameter is strictly less than r. And here's an example. Consider a set, a non-empty set X, and equip it with the discrete distance, which is 0 if X equal Y and 1 otherwise. And consider the ball of center A and radius 1. We know from a previous video from section 1.1 that with respect to this special distance, the ball of center A and radius 1 is reduced to the center. So BA1 is just the singleton A. And the diameter of the singleton A is 0, of course, because the distance between A and itself is 0. So whereas twice the radius is 2. So we don't have equality here. Okay, and of course you can give other examples if you like. Now for the diameter of B prime is same proof, triangle inequality, and here's the counterexample. Same thing, take the discrete distance on a set having at least 2 points. So the diameter of X in this case is what? Is 1, because any 2 distinct distances is 1. So now we know from section 1.1 in the examples that B prime, the closed ball of center A and radius 1 is the whole space. And so the diameter of the closed ball is 1, whereas twice the radius is 2, so we don't have equality. Now, question E, we have to prove that a set is bounded if and only if. Bounded means the diameter is finite. So we have to prove that the diameter is finite if and only if A is contained in some ball. Now, we didn't precise what do you mean by ball, open or closed. It doesn't matter, because if it's contained in an open ball, BAR, it's contained in the closed ball, B prime AR. And if it's contained in the closed ball, B prime AR, it's contained in the open ball, BAR plus 1 or 2R. So contained in a ball. So suppose first that it's contained in a ball, then according to question B, the diameter of A is less or equal than the diameter of the ball, which is at most 2R, which is finite. So this is now if the diameter, if the diameter is finite, call it R, it's a positive number, and consider an arbitrary point in A, in small a and capital A. Then the distance between any point X in A and this fixed A is less or equal than the diameter by definition, because this is supremum. So the distance between X and A is less or equal than R, and this means that X is in the ball of the closed ball of center A and radius R. And since X was arbitrary, we get A is contained in the closed ball of center A and radius R. And this is of course contained in the open ball if I want an open ball of a bigger radius. So we proved the equivalence. Now, what are the bounded sets in R? Okay, we have to prove that a set is bounded according to our definition, if and only if it's bounded from above and from below, which is almost clear. If A is bounded in the usual distance, if and only if it's contained in a ball, as you said, of center A and radius R. So in R, it's just an interval, A minus R, A plus R. But now, so if A is bounded, then it's contained in an interval of the form M, small m, capital M. So then capital M is an upper bound, small m is a lower bound. And conversely, if A is bounded from below and from above, then it's contained in some interval, small m, capital M. But this interval actually can be written as an interval of center, the midpoint, and radius, the length over 2. Okay, so we have really equivalence here. So a set A of R is bounded in the usual distance if and only if it's contained in some interval of the form small m, capital M, and therefore this happens if and only if A is bounded from below and from above. Okay, not all sets, subsets of R are contained in such an interval. And last question, we consider two subsets of R2 equipped to the Euclidean distance. The first set was the set of xy, such that x squared plus y to the 4 is less or equal than 1. And we have to see whether it's bounded or not. Now, the first observation is that if x squared plus y4 is less than 1 or equal, then x squared is also less or equal than 1. And y4 is less or equal than 1 as well. So y2 is also less or equal than 1. Therefore, x and y are between both -1 and 1. So this set is contained in a square. And if I want a ball, then of course this square of size 2 actually is contained in the ball of center 0 and radius square root of 2. Because if you just add x squared plus y squared, get 2. So A is contained in the closed ball of center 0, 0 and radius radical 2, and therefore A is bounded. Okay. We don't need to draw what is A exactly. Okay. Now, the second question B actually is the set of xy such that y is bigger or equal than x squared. So, as you should know, this is what? This is the part of the graph. This is the part above the graph of the parabola y equal x squared. And so, if you can, always draw a figure, so to guide your reasoning. Now, it should be clear, intuitively at least, that this part above the hyperbola, the parabola, is of course unbounded because it cannot be contained in a ball. And there are really several ways to justify this in a more rigorous way. Here's one of them. Okay. We observe that 0, 0 belongs to B, okay, because 0 is bigger or equal than 0 squared. And for any x in R, the point of coordinates x squared is also in B because x squared is bigger or equal than x squared. Okay, so these are really points on the boundary, on the parabola. Okay, now I could have taken x and x squared plus 1, doesn't matter. So what is the distance between 0, 0 and x squared? This is the Euclidean distance. So this is just x minus 0 squared plus x squared minus 0 squared. So it's just x squared plus x4. And the diameter is the supremum, so the diameter is bigger or equal than x squared plus x4, but this is true for every x in R. So letting x tends to infinity, we get that the diameter is bigger or equal than plus infinity, so it's equal to plus infinity. And this is a way to prove that B is unbounded. Another equivalent way, just the same idea but expressed differently, we just have to find a sequence in this set escaping any ball. So it has a norm, because in R we have the Euclidean norm. So we have to find if you like, a sequence escaping to plus infinity. So if you consider the sequence xn yn given by xn equal n, yn equal n squared, so this is also the same thing. So this is the sequence on the parabola. The norm of every element of the sequence is just n squared plus n4, and this tends to infinity. And therefore, this is another way to prove that B is bounded. Just find a sequence whose norm tends to infinity. Because if B was bounded, then it would be contained in a ball, and this ball is contained in a ball of center 0, of course, because any ball in R2 or Rn, a ball is contained in a ball of center 0. Just take a bigger radius. And therefore, the norm of xy for any xy in the set would be less or equal than some constant r. So we get a contradiction. So there are really several ways to express this idea. Okay? And instead, of course, we are not obliged to take something on the parabola exactly. You can take n squared plus 1, or n squared, or 2n squared, or anything you like, actually. So the idea is that we have to consider a sequence whose norm can be made arbitrarily large, so it escapes any ball. Okay, so this concludes exercise 4 and this video. And in the next video, I'm going to solve the next exercises. So thank you for your attention and see you next time.